Hi, my name is Christian Kiss. I'm an instrument specialist with Thermo Fisher, and today I'd like to tell you about one of our microplate readers called a VarioScan Flash that does absorbance, fluorescence, and luminescence readings. It's a very sensitive instrument providing precision and accuracy and performance, and to demonstrate this we've decided to use protein unfolding chemistry for UV-fluorometry. To do this, we've picked an assay where basically we're measuring protein fluorescence based on the amount of tryptophan in the protein. There is intrinsic fluorescence based on this, where if you excite at 280 nanometers, you get fluorescence at 350 nanometers under polar conditions. Now, under non-polar conditions, there's actually a small shift in this down to 330, which is not a very big difference, but the instrument, again, is sensitive enough to measure these differences. We've constructed a variety of assays to do this. First of all, we'd like to display the sensitivity of the instrument across a dynamic range. We did this simply by constructing a concentration series of tryptophan across a large dynamic range. We also did this with regular BSA protein to measure the tryptophan fluorescence from both of these. These graphs here represent that the range is very linear across the entire dynamic range. So again, good performance, good precision from the instrument. From these, we took a spectral scan of both the excitation and the emission spectra, just to show that where the emission and excitation peaks are. In particular, the emission spectra show that it comes out at about 350 on the peak. In order to measure the sensitivity of the instrument and the spectral shift, we've designed an assay where we've put the protein concentration into different concentrations of polarity. This graph over here shows the results of this, where basically your red line is going to be in polar conditions. And if we look at the peak, it is centered around 350 nanometers. If you take non-polar conditions and add less of the acid to it, you turn that into a non-polar condition, of course, and you shift the peak over to 330. And as you move those conditions more towards non-polar conditions, you see that the purple and green lines represent almost no acid or non-polar conditions, and thus your shift from 350 to 330 nanometers. With fluorescence in BSA protein, it's a slightly different effect in that where you're going from polar to non-polar conditions, rather than seeing a shift from 350 to 330 nanometers, you get a quenching of the tryptophan fluorescence signal instead. So essentially the same thing was done. The protein was unfolded and placed into a variety of different concentrations from polar all the way to non-polar conditions. And both of these graphs represent that. Again, when you're in polar conditions, as represented by the purple lines, you have very strong signals from the tryptophan fluorescence, but as you expose the proteins to more non-polar conditions, you essentially quench or eliminate that signal and reduce it to much lower levels. And these are represented by the lines down in yellow, orange, and red. To further demonstrate the sensitivity of the instrument, we also wanted to look at the effect of measurement time in the collection of fluorescence data. Normally, by default, about 100 milliseconds of time is used to collect fluorescence data. Obviously, if you collect more data, you'll get much better curves and smoother curves. Collecting less may introduce some more noise. As you can see in these graphs down here, they represent collection of data at 300 milliseconds, 100 milliseconds, and 20 milliseconds. So even at 20 milliseconds, which is represented by the more jagged curves, you can still see the structure of the peaks exist, so you can determine relative peaks intensity. And of course, when you go up to 300 milliseconds time, you have very smooth curves. But overall, all three curves are relatively close to each other, and so you can collect a minimal amount of data and still get similar types of results. As one last measurement of sensitivity, we also wanted to look at the effect of a more dynamic process. So whereas the other assays were based on your solutions becoming equilibrated in either polar or non-polar conditions, what we wanted to do is put your proteins in a polar condition, expose it to material that would gradually change that to non-polar conditions, and then watch that over a period of time. These two graphs up here represent the shifts at 330 and 350 nanometers. Now, as you can see, there's a lot of variability on there. With proteins aggregating in solution, the way the light bounces off of those can often cause noise in your signal. So it's very difficult to determine that. However, the source of variation is going to be the same every time you take a measurement, regardless of whether it's at 330 or 350 nanometers. So by taking dual kinetic measurements, we can actually normalize that to produce some nice fluorescent curves and show how the protein changes under a variety of conditions going from polar to nonpolar. So the results of this poster show that the VarioScan Flash is a very sensitive instrument, can work across a large dynamic range of concentrations, and also produce results that are sensitive enough to show shifts between very small increments in your nanometer wavelengths. Thank you for your attention. For more information on the VarioScan Flash, you can contact us at thermalscientific.com.